Szarzak, and this is my basement. So welcome to Physics Underground. In this video I'm going to try to help you understand what voltage is a little bit better. Alright, so what I've got here is I've got a sheet that I've got strung between two tables, and I've got the sheet as flat and as straight as I could. Okay, so what this is supposed to show is just like a flat chunk of space, alright, where there's no presence of any charge. Alright, and so if I introduce some charge, okay, so what I have is I got a little pole. I'm going to take this, I'm going to slide this underneath the sheet, okay? Alright. And so you can see that when I put the little ball underneath, okay, the space is different. So this is supposed to represent a positive charge. And when I have a positive charge presence, I'm going to create an electric field. The electric field is shown here by the fact that now the space now has a slope. Okay, the deal is that we've used this analogy before when we've talked about gravity. Well, now we're going to do it for the electric field. Okay, so if I take some small positive test charge and I put it near the field that's created by this charge, we see that it gets repelled away. So anywhere I put the ball, it just rolls away. Now, I've tried my best to get a stretchy sheet for this, so hopefully this will show up on video. But you can see that, like, the slope of this, see, like, it curves off. It's like almost like an exponential there, so that the slope of the field, it's not as extreme out here as it is near. So it's like steeper near the top, and then it flattens out near down the bottom. So like down here, it'll still repel away, but hopefully, like I said, hopefully it shows up. Okay, the acceleration is a lot bigger up here because a lot greater force, so that the field it's steeper. Okay, so that's our idea for a positive charge. Okay, so if I take away a positive charge and I introduce a negative charge, so I have actually a piece of tungsten here that I'm going to throw into the center there. So now it makes a dip. And so I've got a little depression in the sheet. So I hope this shows up. So if I bring my small positive test charge in, the ball is going to roll towards the little negative charge. All right, so that's the idea. Okay, so you can think of the negative charge as creating like a hole. Okay, whereas like the positive charge is creating like the mountain. Okay, so then let me go back to the mountain real quick because I think it's easier to see on video. Got to do this quick. Okay, so there's our electric field that's generated around the positive charge. Okay, well, what you have to imagine for voltage is represented by equipotential lines. Voltage is electric potential, so a line where the voltage is the same is an equal potential line is an equipotential line. And so you can kind of imagine around here, if I like made like a ring, okay, that I just went around here and I kept the height of my finger constant, what I'd really be doing is I'd be tracing out an equipotential line or a line of equal voltage. I could like take my finger and lower it down, and I trace another path around. And so all I'm trying to do here is keep my finger at the same height on this hill that I've built. Okay, well, that's another equipotential line, another line of equal voltage. The reason that we like to talk about voltage is we say that's a scalar. And so what I mean by that is if I take two, so like they've got two different sized balls here to represent two different charges. So there's like a big charge and like a small charge. Okay, well, even though if I put them at the same height above the hill, they've got different amounts of potential energy because this one's got more charge than this one, but they're at the same voltage. And really, voltage is useful because it can help me predict behavior. See, so if I take both of these here and I let them roll, the rate that they roll off the hill is the same. That rate of acceleration that I get is the same. And we've used this trick before with potential energy becomes kinetic energy, where the mass just factors right out. Well, we can factor out the charge as well by using this little trick of voltage. If I put them at the same voltage, okay, well then they're going to undergo the same change in voltage in the same amount of time. Just like if I took two things of different mass and I dropped them in a gravity field, okay, Okay, they would undergo the same change in distance with the same change in time. They would have the same acceleration, so they undergo the same velocity, change in velocity with respect to time. Okay. Okay, hi. So in this setup, I've got two poles underneath this pushing this up. So this is supposed to represent two positive charges. So this would be a positive charge, and this would be a positive charge. And what you see with the sheet, this is the combined field that you get from the two positive charges. So you've seen the diagram for the field, but now we're going to look at this more in terms of voltage. Okay, so remember the electric field is defined as what would a small positive test charge do if you brought it in. And so with the two positive charges, no matter where I put, here's my test charge, no matter where I put this, okay, it's going to be repelled away from both. Now, technically speaking, if you can see, there's a little dip in between. At this very middle point, it would be an equilibrium, but that equilibrium is what we call unstable equilibrium because with very little displacement. Okay, look at that. It's going to fall right off. So I'm actually surprised I got it the first time. Okay, you just got to get it perfectly balanced. But anyways, so voltage is position within a field, like a uniform position within the field in terms of field strength. And so, like, if I took my finger and I kept it at a uniform height, I could actually trace out a little circle around this peak here or this peak over here. These would be lines of voltage, so equipotential lines. Okay, places where the value of the voltage is the same. As we move farther away, the voltage drops, okay, but I could still take and trace my finger around a line of uniform, we call it like elevation within the field. The analogy is to think of like gravitational potential, where as long as we maintain a consistent height, we're at a consistent gravitational potential. So I'm just tracing out loops where I'm just trying to keep my finger the same height above the ground. And if I take two objects with different amounts of charge, okay, just like in a gravity field, things with different mass behave the same. Well, with this different amount of charge, if I release them at the same height in the field, it's like the same voltage. Okay, so see, they accelerate away at the same rate, even though one would have more charge than the other. That's the idea. Okay, and the behavior is the same as long as I stay at the same line of voltage. Okay, so like, let me just make up numbers. This is really high voltage, so maybe like, you know, right here, this is like 10,000 volts, and well, this would be 10,000 volts too, so you'd actually have two lines of 10,000 volts, and then you'd have another line, maybe down here, this is like 8,000 volts. Okay, this would be 5,000 volts. Okay, and again, the numbers are just for talking points, but high or positive charges yield high electric potential or high voltages, and as you get farther away, the voltage goes down, like with elevation. Okay, so that's the idea with the two positive charges. Okay, so now what I got set up is I've kept one of the positive charges here, but I took away the other positive and replaced it with a negative. So I put the tungsten in there so I get a divot created in the blanket, so like a little valley over here, and then I've got a peak over here for the positive. And so this is the electric field that gets generated around this arrangement of charges. And remember, electric field tells us about the force on some small positive test charge. So if I take my positive charge and I put it near this mountain over here, it rolls away because it's repelled. If I put it closer here to the negative, it gets attracted. Okay, and I can come in from whatever direction I want. I can get repelled away over here, or over here, so on and so forth. Okay, if I go right in between them, all right, so if I start with the positive, it's going to roll right to the negative. Okay, and the sheet's bunching a little bit, so you have to picture this a little bit smoother than this, but you get the idea. Okay, so we got this field straight from the positive to the negative. Remember, all this is opposites attract like charges repel. If I take and I use that idea of an equipotential line or a line of equal voltage, okay, so I could trace around a ring around this positive charge. So here's some value from some positive voltage. Again, numbers are just fictitious, so 50 volts, okay, who cares, doesn't matter. If I go around here, down in the valley, all right, I can trace out a ring over here too, so maybe like down here it's negative 50 volts. So if you're familiar with geography, think like height above sea level versus height below sea level. Okay, but this example shows us something else. All right, so this is like a positive voltage is up here, and negative voltage is down here. 0 volts is actually right here in the middle. Okay, and that's an important piece here is that 0 volts doesn't necessarily mean that nothing's going to happen. It's just a location along a potential difference or a difference in voltage. So I've got like a high voltage over here, 0 voltage, and I got negative voltage. So I still got a change in voltage going along here. So even if I put it right at 0 volts, like right in between, it's still going to roll towards the negative. See, it's still going to lose, excuse me, some electrical potential energy naturally if I let the field do work on it. Okay, so that's the important part here is that 0 volts doesn't necessarily mean nothing's going to happen. All right, that 0 point, it's relative anyway, so I don't want you to get hung up on that. That 0 volts means nothing's going to happen. If I have charges here, I can have a 0 voltage point, but it's still going to cause the charge to behave. Okay, and this is just the contour that we get. We could actually trace out a line of uniform voltage out here somewhere. Okay, so we got these big rings, and then at some point the rings would just go around the individual charges. Kind of like as we move farther and farther away, it would be hard for us to tell if there's even any charges here at all. Okay, so that's the idea. Okay, so I set up my 2 positive charges again, and I think this actually kind of looks better from this view here. I've got the camera set up on the side, so you can really see the peaks over here where you could trace out a line of voltage. Okay, so everywhere along here would be like at the same voltage, and the same thing over here, this would also be the same voltage along this ring. Okay, I could trace out another equipotential line and go around over here. So again, just more equipotential lines, but that's not why I set this up. So what if, instead of 2 charges now, what if I could take and I could put a 3rd charge right in between them and put them at the same amount of charge, so I get the same voltage. Okay, so now I got these 3 little values, but the point is that the differences in elevations from the peaks, you see how this dips down a lot farther now. If I bring this up, okay, it kind of raises up the whole space. And so then if I add in, say, like if I added in like a 4th charge, okay, so like the individual peaks on top of the mountains relative to one another, the differences in height get smaller and smaller and smaller. And so you have to do a little bit of imagination, but like, what if I just kept adding in more and more and more so that these were really like bunched together? So that if I hold the meter sticks that I've got underneath the blanket, it's kind of hard to tell that there's even any individual peaks here. So like, you have to imagine a line of charge all right in a row. What would that look like? What would that do to the space? So this is kind of neat. So you're gonna watch this. So I'm just gonna take my meter stick and sneak it underneath here. I'm gonna put it on top of these 2. So just imagine the meter stick as just a whole line of positive charges. And the way that we do that was we would charge up a piece of metal, a flat piece of metal positive. And look what it does over here, how this is now nice and smooth. Okay, so we have a nice uniform slope. I'll show you this from the side here in a second, but just so you can see it, this nice uniform slope everywhere. That's what we call a uniform electric field. Okay, and because now my space, the slope of my space from the perspective of the charge is nice and uniform, the behavior of the charges is going to be nice and uniform. So I get the same force, hence the same acceleration no matter where over the wall, anywhere in this uniform electric field. Okay, and that's going to be very useful to us because it's going to simplify things mathematically. Okay, so this is the same setup I just showed you, just from the side, as opposed to the camera was looking over here before, and you can see the slope on both sides. Okay, so everything is nice and flat. Okay, so you can see that the meter stick just sits on this. We got a nice uniform electric field now that we've generated. And again, the way we've done it is just put a line of positive charges here. Okay, so this is the analog would be to be charging up like a flat piece of metal positively. All right, and if I've got uniform electric field, well then it makes it really easy for me to identify lines of voltage. So like anywhere along this line, this would be our equipotential line, a line of uniform voltage. Down here, this is just a lower voltage. Okay, and I can do the same thing on the other side. So this is a line of equipotential or a line of uniform voltage, and I just move on right on down the line. Now with the uniform electric field, okay, with these straight equipotential lines, it makes it a little bit easier for us to show something else. Okay, so you got to picture the slope of the electric field goes down here, and the line of equipotentials like this. The line of voltage is perpendicular to the electric field. Okay, and that's a property that's always a case. It's just a little bit harder to see when you've got these curves going on around single charges. Here it's real easy to see. So like it slopes downhill. The equipotential line is right here. This is my line of uniform elevation within the field of my equipotential or equal voltage line. Okay, I could take and put charges anywhere along this line and they're at the same voltage to start on both sides. Okay. Okay, so I've gone and replaced my line of positive charges. This is my analog for a line of negative charges. Okay, so just think if I took a piece of metal, a flat piece of metal, and charged that plate up negative, I would get a nice uniform field around it that looks like this. Okay, so it would dip down. So these would all be negative voltages. Okay, but the fact that they're negative, that part doesn't even matter. It's just if charges undergo a change in voltage, they're going to undergo a change in potential energy, and hence they're going to undergo a change in kinetic energy too. So like if this is negative, well, remember opposites attract, okay? And so we take our little small positive test charge and we see it accelerate towards this negatively charged plate. And what's cool about it, okay, hopefully this shows up on camera, but because the slope of this is constant, okay, it doesn't really matter. So they just kind of move together. They accelerate at the same rate down towards the negative charge. Okay, so we've got this uniform slope. That's the electric field. All right, and if you remember from what I was just saying before, the lines of voltage, equipotential lines, they're perpendicular to the electric field. So like this would be a line of uniform voltage. So this would be a higher voltage. This would be a lower voltage. But again, now I'm talking negatives. Okay, so maybe maybe this is minus 60 volts, and this is minus 80 volts, and minus 90 volts, like that kind of thing. Same thing happens over here. Okay, so maybe this is minus 90 volts, 80, 70, 60, minus 10 volts, minus 20 volts, minus 30 volts, minus 40 volts. I hope I said that right over there too. Okay, so that's the idea, right? Okay, so last but not least, I have the setup where this is supposed to represent my positively charged plates, and then this is my negatively charged plate, so I get this nice uniform field in between the two. So I have a very steep slope, but I've got a very flat field, so a very uniform electric field, so that I can take and I take the two charges and I put them at different positions in the field. They're both a little positive test charges. They're both going to be moved towards the negative plates. Okay, but hopefully you can see that one never really catches up with the other until they actually hit the plate. Now once they get to the plate, we'll deal with that later. That's not so important here. And it doesn't matter if we've got different size charges. Okay, so they're still going to behave the same way in the field because that field is uniform. Okay, and so once again, just to emphasize, all right, so the electric field is pointing this way from the positive to the negative plate. Okay, equipotential lines are just perpendicular to the field. So this would be like a line of very high voltage. So maybe this is like positive 50 volts, positive 40 volts, so on and so on and so forth. At some point, 0 volts, negative 10, negative 20, negative 30. And again, I'm just making up numbers off the top of my head. Okay, the numbers don't really matter so much here. Just the differences is positive voltage, negative voltage, 0 voltage in the middle for my positive plate, my negative plate, where I get this uniform electric field, and hence lines of voltage are going to be perpendicular to that field. So that's the idea. Okay, and so last but not least, I wanted to just show the positively charged plate and the negatively charged plate down here, so that I get this nice uniform electric field in between. So I got these nice easy places to identify lines of equal potential. Just so you can see it over here, again, our little positive test charge is going to be attracted to the negative plate. If I was over here on this side, okay, it will get repelled away. And then, and most importantly, nice in between, I have a nice uniform slope. Okay, so I get a nice uniform field. So if I take my two balls, okay, you see that they both fall towards the negative plate, but they fall at the same rate of acceleration. The last little thing I wanted you to see is, well, over here, this is the edge of my table, and this is the edge of my table, which corresponds to right in between the two plates. So I just got a little board here. If I put it in between, you can see that I've actually got 3 locations. So right here, and then right over here. So these would all be at the same voltages. It'd just be locations, okay, of equipotential. And this little spot right here, really the analog that I want to show you, this would be like 0 volts. So this would be like a high voltage, 0 voltage, and then down here would be like the negative voltage down at the 2x4 that's hanging. Okay, so remember, 0 volts doesn't mean nothing's going to happen. You have to look at changes in voltage to really get a prediction of how an object is going to change its energy. All right. So that brings us to the end of the video, and if you've sat through all this so far, I figured I'd at least give you a tour of my basement, given that physics is kind of gone underground. Okay, in case you're wondering, this is my rocket ship. My dad built this for me when I was a little kid, when we were really poor. And my parents didn't have any money for Christmas presents one year, so my dad saved scrap parts and built me this little rocket ship. So now Ian and Lydia both have this to play with. It's Lydia's Minnie Mouse tricycle. This is our bowling lane. We've got bags set up down here. Over here we've got playground equipment for the kids, trampoline, little fun area, and then over here, it's still under construction, so I can't show you just yet, but this is my music room. So coming soon. Well, anyways, thanks for watching, and I'll see you out there somewhere. Bye.